Okay, I think we can start, guys. So a little introduction about myself. I am Manu, Secretary of Internal Affairs at IEEE Student Branch. As a part of ILLUME, that is our CAS week-long events, we'll start with our PCB design workshop. So here it is. So yeah, coming to PCB design, does anyone have any idea about it? Prior knowledge? Come on, what do you think is a PCB? Anyone? It's fine, you can drop it in the chat box. Okay, I don't want the session to go dry, just will be interactive. Yeah, printed circuit board, yeah, exactly. Yeah, what does it do? Like, can you please elaborate on a little bit? Yeah, that's the full form. PCB stands for printed circuit board. And a little elaboration maybe should be good. Okay, that's fine. Okay, yeah. Here. Yeah, before we begin, just a disclaimer, we'll be only covering till designing the printed circuit board and not the manufacturing part. Okay, just till the how to generate the Gerber file, only till there. We have an answer here. Printed circuit board generally mechanically supports and electrically connects. Yeah, that's great. That's great. That's what it is. Yeah, cool. So yeah, we'll begin. Yeah. So yeah, since some of you answered, I guess we are good to go with the session. Yeah. So here we go. So basically, a PCB is a printed circuit board. That's a full form. It's an electrical circuit whose components and conductors are contained in a mechanical structure. That the thing where all these designs are made, that is a mechanical board. That's a mechanical structure. What is called. And what do you think it's made up of? It's made up of a fiberglass, composite, epoxy, or other laminating materials. The conducting materials are etched, or nothing but we can say printed on the board, connecting different parts of the PCB. Different parts may include the ICs, transistors, resistors, or capacitors, whatever it is. Okay, that's about PCB. What is a PCB? Okay, coming to why PCB. Why PCB just attributes to its advantages. What are the advantages of PCB? I have listed 4 of them, but there are many. One thing is that it's compact in size and saves wire. Yeah, as you know, there are before there were, instead of using a PCB, people were using tag boards. Tag boards are nothing but where edges are of conductors. The bottom is nothing. Bottom is just the wooden plate. So what happens is if you have to make a connection, you have to just use those side conductors. That's all. The soldering thing, and it's all a mess. It's a huge mess. So some great person came up with the PCB so that it's compact in wires and saves a lot of wiring. In tag boards, you basically connect the wires. Here, the interconnection between the components is made through copper tracks instead of using a number of current carrying wires. Yeah, it makes the interconnections less bulkier than what it will be using a wire. Also, coming to the next point, it's tight connections and short circuits are avoided. What happens in other circuits is you connect a resistor to another capacitor, whatever it is, through a wire. Sometimes you don't even bother if it's connected tightly or is it loose contacted or short circuited. In case of PCB, it's nothing like that. It's all connections are tight and short circuits are always avoided. And also easy repair and diagnostic. Say suppose a transistor isn't working on a PCB, you can always replace it. You just use a multimeter or something, just test it out. If the flow is on or off, then basically your polarities are proper or not. In case of any damage, the components are easily repairable. Then we have someone here. Yes, Achilles here. Okay, continuing with the slides. Third point is easy repair and diagnostic, and next is immune to movement. Say suppose in a tag board or breadboard, whatever it is, if you just shake it or shake the breadboard, there might be a chance few of the components might fall off. See, the breadboards and all that are used for prototyping. And it comes to PCB, that's say suppose you're working on a project and you design a prototype, you wouldn't go for a PCB on the first place. You would design the CAD file or whatever it is, then implement the circuitry in a breadboard. Then if the circuitry and all is fine, then you'll approach the PCB, the designing part. So breadboards are usually used for prototyping and stuff, and not for the final stuff. So the in PCB, what happens is the components, all the components of a PCB are held fixed to the board. They're immune to movement. Basically, how this is done? This is done by solder flux, which does not allow them to move irrespective of the movement of the board itself. See, unless and until the board moves, these components doesn't move at all, or there is no point because it's already soldered or held fixed to the board. Yeah, apart from the advantages, we have a little of disadvantages. That is, it's not suitable for high current applications. A large amount of currents, like maybe amps, a lot of higher maybe more than 2-3 amps, it's not favorable, as the copper tracks are very thin and they're good only to carry the less amount of currents and not heavy currents. So these copper tracks, in this case, straps will be heated up and cause problems. If the copper track heated up, the boards itself heated up, and it's a problem. So since we have a lot of advantages than the disadvantage, why not go for a PCB? Coming to the types, we have different types of PCB. As you can see in this slide, we have listed 2 types. One is single side and another one is double side. In a single side PCB, as you might have guessed, it's only copper tracks or the connections are made only on the top layer. Okay, so the one side of the PCB is used to connect different types of electrical components, maybe resistors, capacitors, or inductors, or whatever. In double side, what happens is a thin layer of conducting material, that is a copper, will be present on both top layer and as well as bottom layer. Also, we have to make sure in double side PCBs that both top layer and bottom layer are connected. How these are connected? These are connected through something called as via. We'll be discussing it further. Okay. So that's about single and double. You can see the picture in this single layer. This is called the substrate, the mechanical board which I was talking about, and this is the copper layer which is a conducting. Okay, we have someone here. Yeah. Moving on, this is a substrate which I was talking about as a mechanical part. This is the copper layer which is used to conduct, and this is a solder mask. Solder mask is used to basically prevent the oxidation of copper. Whatever the copper is, if the copper is exposed to air, it gets oxidized and will be not as good as the one which is not. So the solder mask is used, and also it is used as insulation. In double layer, as you might have guessed, this is a mechanical substrate. This is a top layer of copper, and this is the solder mask. This comprises the top layer, and this whole thing comprises of a bottom layer. How these are basically connected? It's done through vias. And there are also like different types, which are multi-layered, flexible PCBs, and rigid PCBs. In multi-layered, it's not just 1 or 2 layers. The board will be having at least minimum of 3 layers, minimum of 3 layers, but more than 2. It means the type of PCB have at least 3 conductive layers. For securing the board, glue is sandwiched between the layers insulation, which ensures the excess heat will not damage any component of the circuit. That's what. So you might have seen in the boards like Raspberry Pi or Raspberry Pi and any other development boards. These boards will have basically number of different layers of PCB connections, copper tracks. This is used in order to increase the mechanical strength as well as in order to reduce the size of the PCB manufactured. That's the one intention of multi-layer. And next, coming to flexible PCB, it's also known as flex circuit. This type of PCB uses flexible plastic materials like polyamide, PEEK, that is polyether ether ketone, or transparent conductive polyester film. This circuit board is generally placed fold or twisted. See, if you guys have worked on a Raspberry Pi or something, you get a camera module, right? Camera module and a display board. In those, your connections are made. You're basically using a flexible PCB, where you get a strip which that comprises of thin copper tracks, which can be easily bent. These are flexible, and this can be inserted to the Raspberry Pi, and you can get whatever the desired output is. Yeah, that's about flexible PCB. Moving on to rigid. Rigid PCBs are made out of solid material which does not allow PCB for twisting. That's as the name says, it's rigid. Same as flex PCB, rigid PCB also has different layers of configuration like single layer, double layer, and multi-layered as well. The one thing is this PCB cannot be bent according to the shape of base. That's why this PCB is known as rigid PCB. The name itself says it all. Anyone has any doubts so far? I guess we are good to go. Yeah, moving on. We have PCB according to mounting system. These mounting system, there are two types. One is through hole and surface mount type. In through hole, what happens is you get in labs which you use the resistors, capacitors, and all. These in the PCB, the holes are drilled, and the components like resistor, whatever it is, it's inserted. And, okay, we have someone. Okay, in through hole, the PCB holes are drilled, and your components, like say suppose it's a resistor, it will be inserted, and beneath that, where your pins are, where your pin comes out, the soldering is done below and not the above. As you can see in the picture, the resistors are inserted here through these holes, and beneath that there'll be pins coming out, which will be soldered, and the extra pin of that will be cut out. That's how it's the through hole manufactured. Through hole PCB is manufactured. We have in this type of PCB, we have to make a hole using drill on PCB. These holes leads to components are mounted and soldered to pads situated. Pads are nothing but the holes where we insert the components. That's called as pads on the opposite side of PCB. So when you look at the bottom of the PCB, what you find is these legs extending out, which are actually soldered. What happens is when they insert it inside, you get the extra part, which once you soldered, those resistors stick to the PCB, and beneath the extra leads will be cut out. Okay. So next comes the surface mount PCB. In this, components are small in size, like SMD as the name suggests, surface mount devices. You might have studied in earlier classes of electronics if you have opted. SMDs are surface mount devices. SMDs are very tiny. It's sometimes hardly visible to our naked eyes. So these components, these are SMD devices. These will be there'll be no drills. They'll be placed on the board and applied a solder paste. Okay, these are small components, have very small leads or no leads at all, and required for mounting on the board. Here in this technology, SMD components directly mounted on the surface of the board are not required to make a hole on the board. That's what. See, these components are so tiny that you can't manufacture this PCB using your hand. You'll require some components in order to place that particular component. Say suppose it's a resistor, you just can't take it in your hand and just place it on the PCB. You'll need some tweezers or something like that. It's mostly manufactured by robots, but again, you can do that. Applying solder paste and it's dried off. That's where you get the surface mount. So you might have a doubt when to use surface mount and when to use through hole PCB. When it comes to mechanical strength and that is your concern, you better go with through hole PCB, and surface mount when it's mostly digitally oriented and your mechanical stress isn't your concern. That's where you go to surface mount PCB. Surface mount is usually for the boards which includes a large number of circuitry which has to be mounted on a single small board. You go with surface mount device, surface mount PCB. Yeah. Yeah, as you might have guessed, what might be the next thing we are looking into? Any guesses? Any guesses? Look at the meme. Look at the meme. What is the one word which catches your eye? Exactly, Pravanjana. It's terminology. Yes, that's what we are looking into. Moving on. Here are some of the basic terminologies which we'll be looking into. There are lot of things, but I have filtered a few, and the most important ones I have listed here. One is the annual ring. Annual ring is a copper area around the drill hole that serves as ensure good connection vias and provides spacing for solder mask applications. Vias is in the next slide. Coming slide. Annual ring is that when you make a via, that is connection between top layer and the bottom layer, you need to provide some extra copper surroundings around the via, so that it gives a good connection for the wires. That's where annual ring comes into the picture. You might have seen when there's a hole, it's not just a hole, it's around that there's a golden ring around that. That's what is called annual ring. Next comes the copper weight. It's term used to describe the amount of copper on an external or internal layer of the board. That's what copper weight is. It's just a small terminology. Clearance is nothing but the shortest distance between 2 points on a printed circuit board assembly. That's a PCBA. The shortest distance which you can measure, that's nothing but that is called as clearance. Next coming, it's a very important thing, design rule check. Design rule check is nothing but say suppose you design a PCB and you make a lot of mistakes in that. DRC, if you click the DRC button, it'll check if there are any errors in your circuit. If whatever you have designed, is there any errors in the circuit, or which are against the rules of guidelines within the specific limitations of whatever it is. Some of DRC is a comparison of your design specification with a set of guidelines within specific limitations, some of which are standards, and DFM, that is designed for manufacturability, parameter ranges within which your design parameters should be selected. Yeah, that's what DRC is. We'll look into that later. Footprint. Footprint is also known as a land pattern, is arrangement of pads or through holes used to physically attach an electrically connected component on a PCB. That's what a footprint is. It's also called as land pattern. It's basically the arrangement of pads. Pads are nothing but the holes which I spoke about. How are they arranged? How are they attached? Electrically connected, and all those is that's basically footprint. Next, going to the ground plane. As you might have seen in every circuit we design or in the labs, will always have something called as ground. Even in PCB, we have this ground plane. For circuit boards, good grounding technique is essential for effective signal routing. That is what is ground plane. Next, coming to the pad, as we spoke this in through-hole PCB. Pad is a small surface of copper in a printed circuit board that allows soldering the component on the board. We take the example of through-hole PCB, where once you get the PCB home, you'll see a lot of holes in that. Those holes where the components must be inserted. Say suppose it's a resistor to be inserted. That's nothing called as that's what is called as pad. Okay. Next is design file. That's what we are generating today. That's our main intention. Designing a file. That's a Gerber file. It's called as Gerber file or PCB design file. So more accurately, the PCB manufacturing should contain information of specifications and images needed by your contact manufacturer to fabricate and assemble your boards. See, when you finish the Gerber file and send it to the PCB manufacturer, you can't just send an image. It's just a top image or whatever it is. It's not at all sufficient. It needs to have a lot of information. This Gerber file, what it does is, it gives you all the details of the board, what are the components and what all to be included and how the board is to be designed. That is what is Gerber file. Next is pitch. Pitch refers to the amount of space between the center of adjacent pads for a component. Pads is also known as or pins, where a pitch refers to the amount of space between the center of adjacent pads. Next comes the routing. This is a very important thing, routing. Once you finish the designing of the circuit, you just can't, that's not the end. There's something called as routing. Routing is the main stage of PCB designing, where PCB trace routing is a process of specifying copper traces that connects the board elements. When you finish the schematic and just next stage, what you'll be doing is routing. In routing, you basically connect one part of the one end of the resistor to another end. You would be doing it in wire in case of breadboard or something, but here you'll be using copper tracks. The way in which these components are connected is called as routing. There are so many guidelines which you need to follow in order to do the proper routing. There are a lot of rules for this. Next comes the sill screen. Sill screen is a layer of ink trace used to identify the components, mark logos, symbols, and so on. You have manufactured a PCB and you get it home, like maybe you get 5 boards or something, and you see the PCB and it's blank. It's completely blank, and you don't know where to fabricate the components on which place. It'll be a bizarre for you. So this sill screen, what it does is, when you design the PCB, there is something white writings done. Say suppose it's a resistor, it's named as R1 for transistorised Q1. Its labeling is up to you. Labeling is done. That ink is called a sill screen. That is basically to indicate the components. If you're using a key, it will be named as Key1, or it's a capacitor, it will be named as C1, or whatever it is. You can even mention the values of the resistor or capacitor using sill screen. It'll be usually in the when the PCB is fabricated, it will be in white ink, white color. Okay. Next comes the solder mask. Solder mask, as I said, it's basically to prevent oxidation of copper, and it gives a good insulation for the board. If you might have seen normal Arduino board or whatever it is, if you touch it, it's not copper what you touch. It's basically the solder mask. Solder mask, it's also known as solder stop mask or solder resist. It's a thin layer of polymer. It's made out of polymer. It is usually applied on the copper traces of a PCB for protection against oxidation and to prevent solder bridges from forming between closely spaced solder pads. That's nothing but solder mask. Next comes the trace. The signal trace on a printed circuit board is equivalent of a wire for conducting signals. Okay, each trace consists of a flat, narrow part of copper file for the remaining after etching. That trace is nothing but the path which you connect from one component to other. That's a trace. The thing where a copper is in a line. The line which connects the component path is nothing but a trace. Via, as we discussed earlier, it provides a means of passing currents from one layer to another. Say, suppose you have a double layer PCB, and double layer PCB, the top layer has to be connected to the bottom layer. It's done through via, where the PCB is literally drilled hole, and below bottom layer is connected to the top layer via through this wire. That's about the terminologies. Next, coming to the few of the rules. Yeah, you have to place components to avoid long traces. There are many rules to be followed, but some of them I have listed here. Use a ferrite core on the DC power cord to reduce EMI, and avoid via and pads in the path of critical signals, and so many rules. And there are quite a few. Labeling is a must. Labeling is a must because it solves the confusion when it's manufactured. Labeling is nothing but creating a silk screen where the components are actually named, resistor as R1, capacitor as C1, transistor as Q1, and so on. 90-degree bends are not recommended. Instead, straight lines with 245 degrees are preferred. This is because when the current flows, when it takes a sudden 90-degree left or right, it creates a high impedance. In order to avoid that, we prefer either 45-degree or an obtuse one. Avoid wires going through silk screen when labels are being added. That's what silk screen. These tracks shouldn't go above the silk screen. What happens is silk screen is insulated. it doesn't conduct at all. So, and also silk screen, if it goes, it basically spoils whatever you have done. Silk screen is basically the writings, right? So if something is gone, it's seen as scratched. That's what. Power lines have to be kept comparatively thicker. That is because it will be carrying power, and there'll be heat dissipation and all that. In order to overcome that, we need a thicker power lines. Yes, tools everywhere. Always there, sir. Yeah, here are some of the popular softwares which can be used to design a PCB. Out of which today we'll be going with EasyEDA. That is because it runs on cloud, and also it is more convenient than the other softwares. And also you get the cloud. You can share it with others, the designs, and yeah. One is EasyEDA, other is Eagle, Multisim, Altium Designer, KiCad. Electronics people might have used other designing software for maybe simulation or stuff. We'll be going with EasyEDA. Yeah, so let's dive in for the actual designing. Okay, so here what we'll be designing today. This is a transistorized PCB. For this thing, we'll be designing a circuit. So, okay, we have a couple of doubts, I guess. Yeah, no, nothing. How was it so far? Could you able to catch up? Are we good to go? Awesome. Yeah, we'll dive into EasyEDA now. Okay. Just okay. Yeah, I get it. Yeah. Just go to this site, EasyEDA. The ones who doesn't have an account, please do create one. Okay, I'll presenting again. Just I'll give you 2 minutes to create. Okay, can you see my screen? I hope you can see my screen. Okay, yeah, cool. So this is a page where you should be landing. Okay. Yeah, cool. Okay. This is a page where you should be landing. There are a lot of options. There is a version for you to download as well. But for now, we'll go with the online tool, online PCB designing tool. So here you see login or register. If you aren't a member, do register. I'm already a member, so I'll be going with login option. Login, continue with Google. And I have these options. I'll go with my account. And yeah, I am logged in. Once you're logged in, just here there's a top this EasyEDA designer. Just click on that. So far, are you with me? Does everyone have an account now? Okay. Yeah, cool. Everyone has an account, and they must be having something like this page. Okay, let's move on. So this is where you'll start with this is where the home page of once you logged in and go to the EasyEDA designer. So here is a new project where we'll be beginning with, but let's hold on for now, and I'll just explain this page a little bit. Here is tutorials of basic things, what you want, or how we'll go further and all. Video tutorials is also available for the ones who need it. And here is a menu bar, and most of the things will be taken from this. If the components which you're looking for is not available, you can always go to libraries or parts. Parts will take you to another page where you can order parts. We'll just not go there. Libraries, you can just type the word Say suppose you need a capacitor in the search, and you get a lot of capacitors here. So if you click there, you get the circuit symbol, and how will it look in PCB, and also on in real life how will it look. This is how it is. Okay, you can search basically anything. It can be a resistor, and you get a lot of resistors. Yeah, and basically you don't have. Okay, this is something else. We go for a transistor. Yeah, you get a lot of transistors here. This is a NPN transistor. We'll just not go too much into it. We'll be settling with these things. That should be good. For the okay, now since you don't have any projects now, just go and click on new project. That should pop up this screen. Owner name, this should be your name, your Google account name. Okay, then you can give a title. My PCB. Can give any name, then any description. This is my PCB design. Okay. Next, save. And there you go. This is a page where you design the schematic. Is everyone with me till now? Have you got this schematic page? Basically the sheet. Yes, that's awesome. Yeah. Remember the CAD days where you used to do these kind of things, the designs and all here. That's kind of similar here. This is a sheet name, company. Your company can edit this, the date, the drawn by the name of the person. That's me, Manu MB. Okay, let's hop in. So as we said, we'll be doing this circuit. Can anyone tell me the components which we will be needing? Transistorized PCB. We'll be having approximately 7 to 8 components. That's all. Just to get a hold of this, we'll be designing a simple circuit. Then we'll go for a complex one. Yes, capacitors we need. Yes. All right. Yeah. I can answer. LED. Yes, definitely. We need an LED. Definitely. Yeah. Okay. We'll just take off the parts. Go to here. First thing we need is NPN transistor. This one looks like an NPN transistor, doesn't it? I'll zoom in a little bit. This is a transistor, yes. For simplicity's sake, I'll just remove the name. Okay, before that, I didn't introduce you to this page, right? Okay, yeah. So this thing is familiar for you, and so is this. Here is the wiring tools. Basically, when you have to connect different components, you use this wire, and this is VCC, and this is 5 volts, and this is ground, and this is other ground and flag ground. And these you can include image. This is drag, and this is freehand, zigzag, text. You can include text as well. And these are some of the parameters: the background color, visible grid, yes, the grids, this, and all that. Let's just not talk about that right now. We'll just do the schematic. Once we have the transistor ready, we'll take the LED. Yes. After LED, we need few resistors. Resistor is here. Yes, one here and one here. Once we have the resistor, we'll take the capacitor. Okay. In this circuit, as you can see, there's a switch. There's a push button. We also need that. Okay. Push button. Okay. You have push button over here. Yes. Once you place it, for simplicity's sake, we are just removing the names. We'll name it later. Okay. Now to make the connections. Once this is ready, we'll just keep it. Okay. See, what if you have to rotate this? You have several options here. This thing rotate left. This thing rotate right. This is a mirror image, that is flip horizontal. This is flip vertical. You have those options. You can click this and it will rotate. What if you want a shortcut? There's an in your laptop or a computer, press R. Okay. Okay, it rotates. Pressing R rotates. So this is how we need to design a circuit. We'll place the components. Yes. This also need to be rotated. Yes. This also. Yes. Okay. Now, if anything else is needed, we'll just add the parts later. For now, we'll just do the wiring. Just connect this to this, and this to this to this. Okay. Hope you guys are following. Yeah, this looks pretty. Okay, there's a small one. Yeah, you connected this, and you need something called as a power supply and ground. For that, what you'll do is we'll use a connector. This thing will connect the power supply externally. Will not just include it in the circuit. There are two types. one connector. This connector will provide you the screw terminal. CON and TH, whatever it is. This thing will give you the screw terminal when it's manufactured, and the above one, this thing will give you actually the what is it? Female headers. Female headers you'll be seeing, you'll be having it in Arduinos and stuff, where you insert the jumper inside that. That's what is HDR-F, the hyphen 2.5 or whatever it is. So we'll be going with the female header thing right now. You might ask where you'll be using screw terminals or screw terminals or header. See, when mechanical stresses are concerned, we usually go with screw terminals, where you open the screw, insert the wire, and just tighten the screw. That time the wire held fixed to the screw terminal. Therefore, it doesn't move. In female headers, if a circuit is not the bother of mechanical stress, then we can go with the female headers. For now, we'll just remove this. We need to rotate this, so we'll do this to the mirror image, bring it closer, just go to the wiring tool and just wire it up. Here we go. Yeah, so this is our schematic, guys. So yeah, half part is done, I can say. Half part of designing a PCB, maybe I can say it's done. Okay, can anyone explain this circuit? Okay, yeah, I'll explain it. This circuit, basically what it does is when the switch is closed, this LED glows up. And as and when you release, this LED just fades away because there's a capacitor over here. Can you see this guy, capacitor? This guy is responsible for the fading. Once you release the switch, it doesn't automatically switch off. It just fades and then switches off. Gradual off, you can say. Basically, that's basically the circuit. Once you're done, just save it. You should get a saved successfully information over here. Then comes the difficult part. Then you up top here, can you see convert to PCB here? Okay, we'll click on that, and that basically takes you to the page where you get the components as SMD parts, and there's a mechanical board here. Just click escape here, and there you go. Okay, this part is called as routing. No. This part is called as assembly. First, what you need to do is check check these wires, blue wires are there now. That thing shouldn't overlap. Try not to overlap it. If that's overlap, it's a big problem during routing. So I'm not encouraging auto routing, because auto routing takes a lot of time, and it's also sometimes isn't right, and because it sometimes work and sometimes doesn't. After half the way, it says auto routing couldn't complete because of some error or whatever it is. uh, Auto routes are usually recommended when the circuit is simple and could finish easily. Some small circuits usually go with auto routing, but when it comes to a double layer of multiple layer PCBs, and you can't do auto routing, that time it's a very good, it's a must choice for go with manual routing. Manual routing is you doing the routing. Auto routing is just you go there and click auto route, and your job gets done. That's what is auto routing. Auto routing, it takes a lot of time. You have to be very patient. Even though manual routing is also a tedious job, you have to bear. We'll be organizing components first. It'll take a little while. This takes a lot of time, guys. Yeah, see, when you have to rotate this, it's same as the one which we did in schematic. Just rotate. That's how you get it. Doesn't overlap now. Just click rotate. That's how it's done. Okay, one more thing, one crucial point in PCB designing is try as much as reducing the space. It's better if you reduce the space while manufacturing a PCB. That's what is one of the rules. Takes time. Yeah, once we organize stuff, we'll be bringing this thing inside this purple color thing. That is basically the mechanical structure. Right now, you can see these key R1, LED, C1, Q1 are literally huge. You can reduce their size. I'll be telling you once the routing part is done. Yeah, it takes quite a little time. Just bear with me. This looks fine. Just try bringing this inside this. This huge will okay, when you click on the key thing, right side, you'll find line width, height. You basically go to height and reduce the size. You can see it's reduced. It's too small. Maybe I can just change it to 20. Yeah, 20 should be good enough. We'll place it a little there, over here, and change it to 20.0. Okay, placing it either horizontally or vertically, it's up to you, depending upon the routing techniques. If whichever is convenient, go with that. And the naming, just make sure it's named all properly. R2 is there, you have key 1, R2, and placing also matters. For a clean and neat design, just if this is pointing upwards, let this also point upwards. Let everything be uniform. Just click this. The yellow thing which you can see, key1, R1, H1 and all, those are nothing but the silk screen. That those things will be etched using a white ink, that is called your silk screen. Let me just decrease the size. And just rotate it. Are we done? We have this LED thing. It's a quite big. Just change it to 20. I guess we can start the routing part. Better, we just, this thing fits window like this. That's really helpful. So we can start the, yeah, here PCB tools, we have track, that's what we're drawing right now. Then there's a pad, which you need, which is used to make hole. And this is a wire where you used to connect top layer to bottom layer. And this is text. I'll be using this later. And a few more things will just come across later. We'll start with the track thing. That is, come on, we are starting with the route, manual route, connected, and connected, connected, connected. You better move it this side, yeah. And this one here. Okay. And we'll continue the routing. This connects here. This connects here. This one goes here. Goes here. Yeah, this one you can't just bring it this way. There you go. Are all parts done? Okay. Last one. And it's almost done, guys. We're finishing it soon. Yes, routing part is done. We'll move this a bit this side. Yes, it's pretty much done. Okay, now I'll tell you the. You might have seen in Arduino or other development boards, you'll be having the holes at the corners. That is basically for mounting. We take this thing. Sorry, we take this. This is called hole. We create a hole, small hole. We'll just create one hole for now, as I didn't want to increase the size. Okay, so one hole is done here, and we'll move this a little this side. Okay, this should be good. Okay, now the text part. Here, coming to text. Okay. text part. You can place it here, and you can double click and you can edit the text. I'll name it NISB, enter, and to reduce a smile, as you know, 20. You bring it over here. You are about to see a surprise, but save it. Once you save it, you get the 3D wave. There you go. We have manufactured, I mean designed. Yeah, designed a PCB. How is it? So this is your key, this is your R2, the resistor, this is the capacitor, this is your transistor, this is your LED, R1, resistor, and this is where you insert. Okay, before that, we'll do one thing. Let's close this. As you know, we have to indicate the terminals. For that, take this, copy. Here you do double tap, and this is positive terminal, and this is your negative terminal. Just give minus. There you go. And control C. Okay. Save it, and it's done. You can see the 3D view of it. Yeah, now you can see plus and minus. These white things you can see, those are nothing but the traces, a silk screen. This is a PCB. That's done, and you can change the color as well. Blue to will go with green. This doesn't look that good. Blue looks much better. Shall we try black? Oh yeah, black looks cool, a lot cooler. Yeah, this is all about it. Okay, let me show you the routing part, which I have done much better. Okay. Yeah, this was the routing which I did myself, having a lot of patience, with a lot of time, and made it till here. This thing, yeah, this thing, and coming to the 3D view of it. Here you go. It's more or less the same thing which we designed. This is a through hole transistor which I used. And also you get the 2D view also. Just go here and give it 2D, and you have 2D. There you go. Yes. How was it? How was your first PCB design maybe? How was it? Silence. Can I take that as an amazing? Awesome. Okay, yeah, cool. Yeah, great. Okay, once you're done with the routing thing, you can go to auto route. Auto routing is none of a concern now because we did the manual routing. Then we go for the fabrication. Here we have PCB fabrication file giver. Okay, before that we have to check the DRC. DRC is nothing but design check rule. Where is the project? This is it now. Yes, this is it. So for that, we'll go to DRC, design and check DRC. Okay, here you see there are no errors. Net 6 out of 6, DRC error 0. That means our circuit is good enough to get manufactured. Once you get the DRC error 0, go to fabrication, PCB fabrication, check DRC is done. Why is it asking again? Yeah, here you get the quantity and all the details. PCB price is $5. You can order at GLC PCB. Geba view also there. You can go and check the Geba view. Geba view is nothing but the file which will be sent to the manufacturer. You know what? Copper weight is so and so. You have all the details here. Then our part is still only till here. Manufacturing we are not covering, as we said in the disclaimer part. So this is about this, and yes, here we have the design, and yes, PCB design works. What next? Yeah, this section, yeah, this was about all about the basic and also about the single layer PCB. And next, which will be hopping into is double-sided PCB, a little complicated stuff, and also it's a very interesting topic which will be used in actually in the industry and all that. It's more of a thrill and an amazing job. This session will be taken by Shujan. Over to you, Shujan.
Okay, hi guys. Can you hear me, all of you? Great. So we'll continue. Don't worry, it's just 2 or 3 presentations, and we'll just go right back into the CAD again. We'll see some of the issues with PCB. I mean, it looks really simple, right? Just drag the components there, and you're done with it. You don't really have to worry about how the uh, what the tracks and all looks like. But in actually in industries, or when you really do high frequency PCBs and stuff, there are a lot of things that you should keep it in mind. I just have to ask one other question: how many of you are from EC third years or second years? Because you'll be knowing a lot of filtering and stuff, so it'll be really helpful. Yeah, that's it. I'll just go through some of the important ones because there are a lot of there are probably 15, 16 of the PCB issues, which are really prominent. I'll just go through probably 5 of them. Yeah, 9 of them. So the first thing is static. Like you might have all wondered, like when you get a PCB or even your Arduino, your first Arduino, you get it in a semi-transparent blackish cover. It's called an anti-static. The reason why it's shipped with an anti-static cover is because when if the PCB is exposed to the dust, or to anything that's contaminated, like salts from your skin and from sweating, these salts get accumulated on the on the silk screen, or probably the solder mask. And then when there is EMI, or when there is moisture, they create some static, and they can induce some noise into the PCB tracks, because this solder mask is really thin. So these statics, at high impedance circuits, like probably when you consider 100K impedance input circuits, even a point, probably a small voltage like zero point 0.1 or something can change, probably an MSP, or an LSB, which could, it could be like 1% of the error itself. So at high precision circuits, static is also a problem. And then we come to return currents and current loops. So, like we all have studied, Kirchhoff laws, right? The second law. So the current entering should be, should be equal to the current leaving. So at one point of a circuit, the current entering should be equal to the current entering at the other out, you know, at the other end as well. Sometimes, when because this PCB was quite, very really simple, but when you have very complex circuits, you need to differentiate it, in the sense, on a copper clad is what the PCB is made up of. Differentiate analog circuits on the one side or any side. Keep it a little farther from the digital, just because analog can, just to avoid interactions, and to separate the power planes. I'll get back towards the power plane later on. The return current is, when you have different power planes, there'll be different grounds. So the ground, at the power part of the power plane can be G1 if you consider, and the other part could be G2. So there's a voltage difference. So then, because of this voltage difference, that can be differential impedance that is created for the return current. So your part as a designer should be to create the easiest path for the return current to flow back to the ground. There are multiple ways for doing that. One could be filling it with a ground plane. Another would be using vias and shortening the copper copper trace length. And then we'll come to guidelines. Like you might have all used USP, right? So it uses a differential pair, transmission lines. So there is D minus and D plus. So when there is D minus and D plus, and if you run it, through a PCB really close, what happens is there is a concept called as crosstalk. What happens is a dominant transmission line can induce some of its components, or it can induce some noise into the recessive one, thereby changing the values in it. So what you could do is you add something called as a guard line. It's a dummy track or a dummy copper trace, which acts like a shielding between the two differential pays. So that's what guard line is. And then we have stray capacitance and inductance. This is one of the biggest problems as well. So the length of the copper, the longer you increase, it can, it becomes like a parasite to your PCB. It induces it. If you model it in with higher frequencies or noise, it becomes like an LCR circuit. It can have a inductive component and a capacitive component. These can induce noises, and at some frequencies of your noise, they can become, it can attain the Q factor, or it can go to the resonant frequency, and this is called as ringing. So that's the point of the skin effect. So how do you reduce ringing? Is you add a series resistor in between the tracks at some points, local resistors. What they do is they increase the impedance, but the Q factor, it's, if you see the formula, it's divided by R, right? So it reduces the Q factor, so the damping factor increases, so the noise dies off. That's how you reduce that. Then we'll come to mutual inductance. So if you have two copper, tracks, copper paths or current loops, which two inverted, seam, and if it's symmetric, now they act like two coils, create, inducing a mutual inductance. So they induce current in the other loop, and the other one induces in this. So there is, noise induced in the unrespected one, which shouldn't have happened. So that's mutual inductance. So you need to reduce mutual inductance. You shouldn't make it really symmetric sometimes. And then we have skin effect. So PCB tracks are really thin, right? Are you guys following with me? Yes or no in the chat? I mean, I need all of you to spam it. That's great. So skin effect happens is, why it's, really important, and it's an issue in PCBs. The copper tracks are really thin. So when you have high frequency or ASIC or any sinusoidal components running through it, this due to skin effect, what happens is the current flows only in the surface area. So the cross section of the copper track, even though if it's there, it doesn't get used up fully. So now what happens if you, go through the resistance formula, the surface area decreases, so your impedance increases. So you're effectively increasing your impedance in your circuit, which is really not bad. Because at high sensitive and high precision circuits, it's really a bad thing. And I told about ringing, and then you have decoupling. There is no circuit in this, there is no circuit anywhere which doesn't have noise at all. It's the worst enemy in electronics. And how do you remove it from from the circuit is using decoupling capacitors. So what they do is it just acts like, it's also called as a bypass capacitor. What you just do is it acts like a low pass filter. So it takes off some higher frequency components, because usually if you simulate a software, simulate a PCB or something, the frequency components of the noise will be around 50 megahertz or less than that. So you just figure out what's the ideal frequency, or what's the the average noise frequency, and then find the appropriate capacitor value, and just put it in parallel with that, and it decouples or bypasses the AC components. And for DC component, it just acts like it's a it doesn't even exist at all at high because the impedance becomes infinity, right? So it just for DC component it allows it to flow, and for DC component it sinks it to the ground. And then we have ground plane. I just told what ground plane is in the second one. So any doubts up until now? I mean, this is just I just probably 10% of the problems, but PCB it looks really simple, but actually in practice there is a lot of involvement going in doing a PCB. The reason we'll be doing one complex one, which involves two-layer PCB, two-layer PCB design, because it's really impossible or nearly impossible to do it on a single layer. So almost all of us, like literally everyone, how many are present? 47 of us, all of us have worked with Arduino, right? So I'll just go with Arduino. We'll do a smaller version of that. Like I just did one yesterday. It's almost 65% smaller in volume or in area, surface area, than the regular Arduino, but it's just the same job. It does the same job actually. The reason I've chosen it is because all of us are really comfortable with that, and not comfortable. You have used it literally at everything stage of your probably project, so you can relate to all those blocks. So I've just noted down all the important blocks that I need to include it in the PCB. So first I have is my PSU, my power supply unit. So the way you take the voltage in or your VCC. You can take it to USB or DC jack or VIN. That's the things that are present on your Arduino. I'll just be going with USB because it's really small and it's really convenient as well. Then we have your microcontroller unit. That's your MCU. It will be using Atmega 328P MU, which is an MLC package, MLQ package, I guess. It's a micro lead package something. That because it has 32 pins on the side, and the bottom 33rd pin is your heatsink ground. Um, and then we have crystal oscillator. No microcontroller works with crystals or an oscillator, right? So like the Arduino has a Pierce oscillator, so we need an external crystal oscillator for 180-degree phase shift. We'll go through that. And then noise is just not always present at the power source or at just one part of the PCB. It's almost present everywhere and can get induced anywhere in the PCB. So you need a decoupling, local decoupling capacitor every part of the circuit where you have ADCs or you have DACs, and then if you have noise components which can span over a band, you can use decoupling ladders. And if you have a lot of current loops and all, use decoupling ladders at one point of the time to cancel out the frequencies, to nullify the frequencies crossed by one current loops. And then we have a pin expansion. You hook it up to your breadboard and then you do your crazy, all your circuits. So that's basically it. The circuit is really simple. This is my PSU. The thing is, this is not at all similar to what the Arduino actually is, because you can do your version of Arduino and it can look completely different from this. It's up to you. So if you want to see how actually the design is, you can just Google it out, Arduino or any microcontroller schematic, and you'll get it what the manufacturer has done. Since Arduino is an open source, you'll get it freely. This is my version of Arduino. So this is your micro USB. I've chosen micro because it's really small. So you have these shieldings. These will be grounded, and then you have V bus, D minus, D plus, ID, and ground. One more thing, guys. Do you want me, guys, to explain why I have chosen such, those components? Because there is some thought process that involves, in figuring out what the components you need to involve in your PCB. Okay. Yeah, I'll go with I just explained, because Manu has already explained you how to create a schematic. So there is no point in me explaining it again and again. So just go through how I've chosen and how you can make your own the thought process. So I've taken USB. So these are, if you take the data sheet of any USB, you'll get what are these pins do. So the V bus is the 5 volts that is coming from your USB cable. So I've taken that, and then I've passed that through a ferrite bead. So what a ferrite bead does is, you might have all seen this ferrite bead is the thing that sticks at the end of your power adapter for your laptops and all, cylinder type thing. So what it does is, it's a really simple EMI filter. It's like an inductor. It's like a parallel LCR circuit with another series resistance. The way you find it on the market is, you get a ferrite bead, like 100 ohm ferrite bead. So what that 100 ohm suggests is the series resistance, when you model it as an LCR circuit. What it actually does is, it really acts like a it's basically a low pass filter, but with a very high roll off. So if you do the Bode plot, or if you see the frequency versus the magnitude, that passes the yeah output, what you get is really high roll off. So at certain stage of the cutoff frequency, the impedance becomes so I guess the impedance becomes bigger, because impedance becomes bigger, the resistance increases, but the capacitance at the the pass band, the ferrite bead acts as like an inductor, approximately. But after the pass band, it becomes a capacitor, and then it keeps on decreasing the value of the capacitance. So it basically acts like yeah, the value of capacitance decreases, but then your impedance kind of increases. Likewise, it acts like a low pass filter. Did I make sense, or was it like just gone overhead? I hope it made sense. It just basically blocks high frequency noise components from your PCB, from your power source, because you don't need these frequency components which are noise going into your power supply or your power regulator, because that will reflect back into the of output of the power regulator, and then that will be powering your microcontroller. That's really bad. So that's a ferrite bead, and this whole block thing, these two output capacitors and this IC is from Texas Instruments. The couple capacitors are different. This is a LDO. The reason I'm using an LDO instead of the three-legged AM117, I guess that's the what you regularly use if you want to do voltage regulation from some range of voltage like 7 to 12, I guess, to constant 5 voltage. You can use that. The reason I'm using an LDO is because it's really low noise. LDO stands for low drop out voltage. So what it means is the input voltage and the output voltage, there won't be much difference. So you can give 5-volt input and get a 5-volt output itself, but a regulated one without less noise components. The one I've chosen has a very high PSSR value, power supply rejection ratio, so a very low noise. Since it's really low noise, you don't need actually decoupling capacitors, but these are just output capacitor to, in case there is an flickers, you can just smooth it out. And then another thing is, this is a really sensitive circuit, right? It's really small, and the size of this IC is also really small. And then since these are very low power devices, you need an IC or a power regulator which has low inrush current. So what inrush current is when you power it on, the current synced to the regulator should be really less, or else there'll be a spike in the output, or there can be heating issues as well in the starting phase of the powering on. And then that's basically about your power supply unit. And then I've just added an LED and a resistor, current limiting resistor, just to say when the USB is plugged it in, the LED is on, so it tells the power is on. That's what happens in your Arduino, right? So that's what I've done. And then I've put two flags, or like flags like ground, and everywhere here. So this, when you connect it, see it in your schematic, then in your PCB, all of these will be connected internally. The reason we'll be using this is because it separates it, and we don't need to use that connecting everywhere, the ground, which will be really messy and would ruin the aesthetics probably. So that's why we'll be using these flags. So anywhere you refer to as VCC, here or here, these all be same point on the circuit, which will be interlinked. Okay, so that's what those flags are. And then we'll come to the MCU. Everyone fine with the PSU? How do you choose it? Just a couple of yeses or nos. I'll just go ahead. Okay. Okay, great. We'll just come to the microcontroller unit. And how do you get what circuit should be included? You just go through the data sheet and you'll get it. So the first thing will be VCC. You need to power it on, right? So while powering it on, you can directly connect it to VCC. But I prefer using a decoupling ladder, just in case there is some noise that has bypassed the PSU unit, or has been introduced by some mutual inductance or some other factor, a stray inductance. I just want to bypass it to the ground. So I've used a decoupling ladder. And then this is your R reference. This is the voltage that which is the reference voltage for your ADC converter internally. So I've just put a 100 nanofarad decoupling capacitor and shorted it to ground. again for these are all local decoupling capacitors to reduce noise at every point of your PCB. This is really really important. When you are doing this circuit, you need to find out where these noise components could really affect your your PCB, and you need to involve filtering circuits and comparating circuits and all, right at those positions. And this is the reset, the PC6. You'll get it from your data sheet. So whenever it's pulled high or pulled to 5 volts through a pull-up resistor I've used, the watchdog timer doesn't interrupt the MCU and calls for a reset. But whenever you push this button, it shortens it to the ground. So the PC6 reads 0. So the watchdog timer, the interrupt is called for the reset of the MCU. So that's this part, and this part is done. This is just ground. Any pin that you're not using, it's good to put a no connection flag, because it will be really helpful for the DRC checker to see if there are any issues with your PCB. And then this is the crystal. So how many of you want me to explain this thing, or should I just it's just a crystal circuit. Should I explain it? I'll just okay. I'll just go with it. So internally, it has a PS an oscillator. The input to the output, what is that? Phase difference is 180 internally. So that's why we use two load capacitors outside in series with the crystals series capacitor. So what you're actually doing is you're increasing the capacitance of the LCR circuit. When it's modeled as an LCR, the crystal. So you're increasing the phase by you're decreasing the capacitance. Hence, you're making it more inductive. So thereby, you're increasing the phase the phase shift. So internally, just between these two pins, it's 180-degree. So externally, you put 22 picofarad capacitors in parallel with with the crystal. So that brings 180-degree phase shift. So total of 360. So that's I guess there's two criteria for an oscillator to work, right? So it should be either in 0 or it should be 2 pi phase. So 360. So that's why we have used two capacitors. And how do you get these values? You just go to the manufacturer's data sheet of the crystal. They tell you what's the load capacitance that you should use. Just minus some approximate stray capacitance and multiply it by 2, and that's your load capacitors for your crystal. Pretty much this is all, and this FPC is just like you have seen on Arduino, right? Not Arduino. On your Raspberry Pis, you connect your RPi camera. It's a thin, flexible PCB, right? At the end of it, it's called an FPC connector. Okay, that's what I've used just to make the PCB really small. So that's basically the schematic. Anyone, any doubts with this at any point? Or did I make sense, or did I really didn't make any sense at all? I need some yes or no's. That would really help. Okay, so we'll go with the CAD software, and we'll see what are some important ones that you need to follow. Is my screen visible? I guess it's yes. Mano has already shown you how to create a project, and how to create a schematic and all the PCBs. I'll just go with this. I've just created it freehand yesterday. So this is the circuit, the schematic. What to do is you go to design, convert to PCB. I've done that just to save time, and because a simple circuit as what the transistor circuit Mano did took some 5 to 10 minutes of remapping, placing, and then routing. But when it comes to microcontrollers, and when you have a lot of components, and when it's SMDs, and this space is literally like this is just 4.5 centimeters, and this is just 2.5 centimeters. So that can be really difficult to do. So I've just done it freehand. I'll just go ahead and delete all this. The placing, I'll show how many iterations it took me to find appropriate one, because because every time you do it, you don't get the same output, and sometimes we really suck at placing it properly. And only once you're completely done with the circuitry, you get to know that you have really gone to a point where you can't even make it right. I'll just show you some example why you need two-layer PCB. So you press W and that's your wiring tool. It gives you, so the reason I'm using, circular ones instead of, these, sharp edged ones is because if you use the edged one, and if you create 90-degree or more than acute angle turns, what happens is it at the edge, you can create you are creating actually a high impedance, point for the current to flow. And then with high frequencies, those points can act like an antenna and it can create EMIs around the PCB, which is really bad. So as much as you want, try to keep it, at 45 degrees turns. And if you still want 90-degree turn, some point of your PCB, do a 135-degree turn. In case you want all these details, I'll just, we'll be putting all these, schematics and all the papers that we have referred on the GitHub, and you can take a look at that. Okay, I'll just do a couple of them just in case to show you. Now say all these the connections are done, but then you have some circuitry which you need to map it, this way, and it's showing an into, right? So that's, conflict between two, that is conflict between two traces. That's impossible. How do you solve it? Anyone in the chat? I mean, I could go this way. I could go this long way, get it out here, 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 and then here. But why should we not prefer that? Anyone? Yes, I know. Yeah, that's the right answer. Yes, we use VS. But why? Anyone? I just spoke about that in our the issues. I just I showed it in the PPT. Loop acts like an inductor. Yeah. So there are two things that are happening here. One is you're creating a very long loop. So in return, so the return current would come out somewhere here because this might be the ground, I guess. If you zoom into it, you can see which is the ground pin. Yeah, this is the ground. So this is your exit path, right, for the current. So what you're actually doing is if you have a ground plane on the bottom, you're creating a very long loop of, it acts like a magnet, or it can create, EMF around the PCB. And there are a lot of, these might be ADC pins, and you're inducing a lot of noise into that. So you'll get, it's really just, high precision circuitry is just gone. So how do you go around that? And another thing is you're doing a very long track path. So you're actually creating a very high impedance, for the current to go through, and also you're creating new stray impedances and capacitance, which is actually again wrong. So how do you go around that? So what to do is you use vias, because this give me, I'll just change it into angle to 45. Yeah. So how do I go there? So you just goes at some point. Say there is a pad here, you just can't go through this, right? So go to your layer and objects. Now you are drawing it on the top layer, right? Just hit on bottom layer. Now what you have actually done is you have created a via. Via is just a hole through the top layer to the bottom layer, and it's connected by a copper ring. So you have created a bottom path. So you're on the top, go to the bottom. Now you can freely route without any hassle or problem. Come back on the top. How do you do that? You just hit top layer and you're back on the top layer, and then you connect. Okay, I didn't connect that. Yeah. So basically, this is the reason why you need to use two-layer PCB. Another reason would be if you do it yourself. I mean, I could show you what has actually happened was when I was doing this PCB. You can see these 4 pins. I mean, is it visible for you guys? I'll just zoom it out. These ground, VCC, ground, and VCC. The manufacturer has done such a worse job, I would say, is you need to connect these two together and these two together. If you do that, what you'll be doing is, say I'm doing this. Now you can't actually connect it at all, right? So then then you have to use a via, but that is also really difficult at this point. It felt like it would be really easy to use a 3-layer, but somehow I worked around it and got it done. So that's why you use, you know, VS. Another thing would be, these are called air wires. So these are wires that help you to, route it, but they are not actually connections. And then what I have actually done is, in Mano circuit, he connected all the grounds to the grounds, right? So if this is a ground, he connected it to this ground. But I won't be doing that. I just told that using a ground plane is the shortest impedance path for all the return currents. So what I would do is, since I've this is not completely routed, I'll go to the one that I've completely routed. So this is what something, if you do the routing, it took me really like 1.5 hours or 1 hour probably to do this thing. So if you can see these, or if you just hover your mouse around the parts, it will show you it's ground. I've just left all the grounds unconnected. The reason is I'll fill it with a copper, the ground plane, where all these ground pads are connected to one single copper fill. How would you do that? Did I just make sense? What is reduce the tracking? Oh, I just didn't saw. That's nice. Okay. Did I make sense? Like why I have not connected the grounds just using the PCB tracks? Couple of yeses and nos. Yes. Okay. Yeah. Uh, the reason is I just told you to create a ground plane. How would you do that? So I just want a ground plane on my top. So what you do is go to layers, select top layer, and then come to PCB tools, and there is something called as copper area. Press on this, and you need to select what's the net. So net can be, here I'll be using ground, but in case you are doing some other circuitry and you need you need a VCC plane. So if you see the reason why there are 4 to 5 layers in very complex circuits or high precision circuits is there are two ground planes sandwiched between two it can be an analog power plane and then a digital power plane. It can be any power plane that you want to have it embedded between the layers. That's why there are multiple layers, because it becomes easy for for impedance matching and etc. So here I just want a ground layer, so I just kind of press OK. Then it gives you this tool to draw a polygon across your border. This is the border outline. This will be the point at where the manufacturer will cut the fiberglass to get the PCB. So go around it, create a polygon. Once you have covered the complete border, just hit escape, and magically it fills you with copper. So if you can see, these were not connected, right? But you can see they have connected to ground right now. But still, lot of other, there are still 1, 2, 3, 4 of them not yet connected. That is because I just, while showing the other circuit I showed you, the ground and the VCC are so in alternating positions. It's really impossible even to route them on the top layer. So I wanted another ground layer. So if you want another layer at some point, you just hit bottom, because we just have to create another copper fill, which is also a ground, and hit escape. Now it fills with ground on the bottom as well. There is multiple reasons why you need to have ground. When you have transmission lines, the transmission line and the ground also act like a capacitor, because fiberglass is also a dielectric, right? So it will have some dielectric constant, and it can create some capacitance. Having what is that, a smaller area of how would I, but when something like that is happening, what you do is you find a PCB whose fiberglass dielectric is very low, like because and then the price actually increases when you go too deep into reducing your noise in the circuitry. So basically, what I talked all about was how to reduce noise and some tools and some tricks which you can involve in high speed PCBs. Did someone- Okay. So did you guys like get why I used ground planes and then how to do it? It's really straightforward. I'll just save it, and then we'll see the 3D view of that. Yeah, this is a 3D view. It looks a little bigger, but it's actually 1/3 the size of your actual Arduino. Cool, right? I mean, like once this workshop is done, go home, get your own circuit done or schematic done, do some research, and do your own versions of Arduino and get it manufactured. It'll be really cool, to use those in your own projects. And another trick would be, I would say, tips. As I've used copper, these capacitors, which are actually bigger than the pad length. The reason that is actually not good, because what you're actually doing is not impedance matching. So always use any component which has an equal thickness of your copper pads or copper tracks. Okay, so that way it's just an easier impedance path for the current to flow through. So the best choice would be, I've used, I guess, 3216 package, so that's 3.2. Any plans about market? Yeah, we have actually named it as ILLUME after ILLUME of an ISB. We'll look into marketing later on. Where was I?
Shajan, there is Mustafa is asking for a blackboard. Can you change the color and show it to him?
Oh, okay, sure. Board color.
Yeah, change the
Yeah,
blue. Yeah,
yeah, it
awesome.
looks really. And another thing is, I've done a really poor job, even though it's 1/3 the small. I've left a lot of spaces right here, so you can reduce it in your own versions of Arduino. Yeah, I was talking about the size of the capacity, your components, right? You need to find a smaller one. I've used 3216. Probably the best one would be 0805 or 0402, which is really smaller and could be the same size as your track, copper tracks. And another thing, or you can say a mistake that I have done here is, which you need to know, which you shouldn't do, is all my power lines are, the same thickness as all my signal lines. So the way you find it out is, you go to Google, you just say copper track width calculator, and then go to the manufacturer and see what's the ounce length. Ounce length is the thickness of the copper that they deposit using during fabrication or etching. So find, it'll be for JLC PCB, it's 1 and 2 ounces. So go to that calculator, put its 1 ounce, and then what's the current or amperage that you want your circuit to be. So it's 1 ampere, just put 1 ampere and it'll give you thickness. So come here, this thickness is I guess 0.25 254 millimeter. That's 1/10 of an inch. I guess if you calculate it, will give you like 0.3 0.4 or something. So change this thickness to 0.4. So thereby you're increasing or decreasing the impedance or the resistance for high voltage currents, high amperage currents in the circuits. That's one mistake. And then the other mistake was the size of the components that I've used. It's really not proportional. And then other thing is, keep all the components really close together. These high frequency components close to each other. So this is a crystal. Keep it really close to your MCU. Okay, this is the decoupling ladder. Keep it really close to your MCU. And this is the power PSU unit. I've kept it little far from the MCU just to avoid EMI disturbances. I've removed all the names and just added some reset, because there's a reset button, USB, this is the power on LED, and this is my FPC. I guess that's it with two-layer PCBs. Likewise, you can do multiple layer PCBs as well. So any doubts up until now? We'll be uploading all the schematics and all the Gerber files and all the project files on our GitHub and at NIIEEE student branch, and all the papers that we have referred for reference. Uh, anything else? I mean, you can ask any doubt. We have probably 10 more minutes, 10, 15 more minutes left. Hello.
Yeah, I guess you can ask any doubts if you have. Or are you so shy that can't ask?
Hello, Sujan.
Yes.
So,
Is it?
how do you actually solve the assembly components? Like that you will only get the board, right? Only with the traces.
Yeah. Like, can you repeat it again? Pardon.
Yeah, I just wanted the soldering part. How do you solder onto it? Like,
SMDs. So you
do you
have
have
two
to
ways. Either you
manually
can
do
do
it?
it yourself.
Or,
Yeah, go on.
yeah, that's what I asked. Do you have to do
Okay.
it manually? Is there a way to automate it?
No, there are two ways. One is you can do it manually yourself. So you can order, SMDs. You can't, actually use your
Yeah,
soldering lead and do it with a single one. So you'll be using, hot air gun and soldering paste. So you'll get the manufacturer, whoever does that, has an option called solder stencil, I guess, solder paste stencil. You can opt it, and they'll send you an aluminum sheet with all the holes. You just have to match it to your PCB, and then wipe the spread the solder paste,
yeah.
and that's one way of doing it yourself. And then recently, this EasyEDA is from GLC PCB. It's a Chinese PCB manufacturing company. They also have introduced, I mean, even in India, I guess Lion PCB, many more PCB manufacturing, they have SMT technology where they'll do it for yourself. The way you find it, go to your, there was an option called LCSE, right? I'll just present it to you. Window. Just whenever you're doing a PCB, if you're getting it manufactured from this EasyEDA itself or from JLC PCB, go to LCA parts. Or what you can do is, whenever you're sourcing components here, say you want to place a component here, go to library. Say I'll do micro USB itself. You can see there is this tick option next to the card thing. That means it's available at LCAC. This is a component sourcing company from based on China. You can just, whenever, if you're using it from them, it's really easy. What you can do is go to fabrication, then generate BOM. That's bill of materials. It will give you a list of all the. It's an Excel sheet. Upload it to the what's the manufacturer, and they'll do the SMT process. They'll solder it for you.
Okay. So that means you just need to give them the Gerber files and the BOM file. Is it correct?
And then you also have to, give them, if you go to, I guess, wait, go to PCB and then tools, fabrication. You have pick and place file, right? This is for the pick and place tool, the robot, for it to, drop those components. So these are like X and Y coordinates, in 2D space. So you need to upload all the three of these, to get it manufactured. The BOM, PCB Gerber, and the pick and place file.
Got it. Thanks.
Yeah. Anyone else? I mean, you don't really have to. I guess you can even drop the questions in the chat box. Since we have 10 more minutes left, we'll just go through issues you have. Feedback form, yeah. All right.
Yeah, I've sent
We'll
it.
So all of you, give your feedbacks. It's really important for us.
Yes, please.
Tab.
So yeah, anyone voluntarily would like to tell feedback?
Yeah. One more thing is, whatever we have covered in this this workshop is just the tip of the iceberg. It's really like probably 1% of the PCB design in its entirety. So that's one thing you need to work on it yourself, to get to reach the bottom of the iceberg. And yeah, please, we do live feedbacks. So all of you, please
Exactly.
fill the feedback form and take like 1 or 2 minutes. And thank you.
Thank you so much. Oh, thank you so much.
Thank you.
Thank you. Thank you.